Hello and welcome to this session where we're going to be talking about a research project that started this past fall that was conducted by myself, James Osborne, Elizabeth Tomasino, and Michael Chen. All three of us are faculty members in the Department of Food Science and Technology and also members of the Oregon Wine Research Institute. I work on mainly fermentation and microbiology issues, while Dr. Tomasino and Dr. Chen are flavor chemists working on a variety of different projects. So this particular project, we had a couple of main goals for what we were trying to achieve, and it was kind of a very, not spur of the moment, but kind of taking hold of an opportunity that was presented to us, where we were looking at trying to create a database of smoke compound concentrations in a number of different grapes and wines during the 2020 season. So unfortunately, we were hit with some wildfires in 2020, but this presented an opportunity for us as researchers to gather a lot of data in a very short amount of time that we could look to use for future research projects. So we put together a team to work on this project, to gather grapes from all over Oregon and to gather grape samples from a number of different varieties. So we ended up collecting over 80 samples. This was in collaboration with particularly Patty Skinkis from the Department of Horticulture. She helped coordinate with many industry folk to pick up samples from vineyards all over the state, and also with some of our state extension folk, Dr. Steve Rehnquist and Alec Levin also helped coordinate this project. So the goal was to create this large database of smoke compound numbers from a number of different grapes and wines that we would be able to use for future projects. So this would give us information on concentration of these compounds related to proximity to the fire, to maybe exposure to smoke, as well as if there were differences across different grape varieties. So as I mentioned, we collected lots of different grape samples, and then those grape samples were brought to OSU. Samples were taken from the clusters and frozen for later analysis. And then the remaining grape samples were fermented using microfermentation techniques under standardized conditions so that we could compare the numbers that we were getting. So I know a number of people this year, we did a lot of microfermentations of small grape samples from the vineyards and probably used a variety of different techniques and methods. What we were trying to achieve is using one uniform method for all of the grape samples we had, so that how we fermented the grapes was not an additional variable. It allowed us to have some standard baseline numbers, some standard numbers from these ferments that we could use moving forward. So this is the basic methodology we use for the microfermentations. We collected the grape samples. We requested about 20 grape clusters per sample. We hand destemmed all of those grape samples. Like I said, we had 80 plus, I think maybe 85 samples from regions all over Oregon. We had 12 different grape varieties. So there were 4 white varieties and 8 red varieties collected. And once those berries were all hand destemmed, they were then hand crushed, and we dispensed about 2.5 kgs of the grapes into small microfermenters that we use in our research winery. The reds and the whites were fermented on skins, so a little unusual for the whites, but this would give us a more accurate number of the smoke compounds that might be in the grape skins for the whites as well. So everything was fermented on skins. We followed some pretty standard red wine making protocols, where we added about 50 milligrams per liter of SO2 once the grapes were crushed. We added some yeast nutrients, and then we inoculated with a fairly standard red wine yeast, RC212. The ferments were placed into a temperature-controlled room that we set at 27 degrees Celsius, so fairly warm fermentations. And the microfermenters themselves had a submerged cap system, so there are these gallon jars that we have this plastic submerged cap that pushes down on top of the grapes. And so the ferments would proceed with a submerged cap. This meant that we didn't have to manually punch down or mix up these microfermenters on a daily basis. That again removed a potential variable there. They all were submerged cap fermented for 5 days. So every sample was fermented for the same length of time, so that gave us the same amount of time on the skins, and then they were pressed. The pressing again was very standardized, so we used an identical pressure and time. You'll see on the far right here is a picture of a pressing device with a pneumatic ram that we can set for a particular pressure. And so again, all the samples pressed for the same amount of time, same pressure, so that we have some uniformity. Once pressed, they were settled. We added SO2 to these samples. We didn't want the wines going through malolactic fermentation, given that that's an additional variable. And once they'd settled, we took samples from all of the wines and gave those to Elizabeth and Michael for smoke compound analysis. The remaining wines we settled and racked and bottled a couple of bottles of each. There's really small volumes, but those have been stored away, and the plan is to go back to those after a suitable period of time of aging to remeasure and see if there's any change in the concentration of some of these smoke compounds in the wine over time. So this is a general protocol that we followed. It may be similar to what maybe you did in your own winery, but what it allowed us to do is have a very uniform process and not add any additional variables. So this data set we created, we could really understand the differences in some of the smoke compounds in these different grapes collected all over the state using these different varieties. So we handed these over to the flavor chemists and they took it from there.
Great. So I just wanted to give everyone a reminder about the compounds we're measuring and what they are and what they mean. So free smoke compounds such as guaiacol over here are the ones that you can perceive either smell or through in-mouth flavor. Bound smoke compounds, which are also found in grapes and wine, are when those smoke phenols are bound to sugar. So right here, this is a sugar that guaiacol is bound to. And those ones you can't smell and does not do a flavor. So when we put these two together, the free smoke compounds and the bound smoke compounds, you get the total smoke compounds. And the total smoke compounds is really determining the overall risk you have. Because over time, as wine ages, the bound smoke compounds become converted to the free smoke compounds. But particularly when we measured these wines a few months ago, there would be more bound smoke compounds than free. So just a reminder what those are. Presently, when we did this analysis, we did not have the ability to directly measure the bound smoke compounds. So we did something called acid hydrolysis, whereas you take your wine sample and you lower the pH quite low. And that helps break a lot of the sugar bonds to the compound. So it breaks the bonds here and creates more free smoke compounds. And we call this an estimate of the total smoke that you have. And we call it an estimate primarily because it's not a direct measurement of bound. We're essentially trying to break these and then measure everything as a free. So what we did for chemical analysis is I measured the grape samples prior to fermentation. James took samples for us. And we measured the free smoke compounds of those grapes. And then Dr. Chen in his lab measured the wine samples. And for the wine samples, they measured the free smoke compounds, and then they measured the total smoke compounds by running that acid hydrolysis. So again, that estimate of the total for it. And this is just an example of one of the chromatograms we use for measurement of things. Each of these are some of the different smoke compounds. So I'm going to sum up what we found. First off, the free smoke phenols in grapes. If we look at this biplot here, the X's are the averages. The whiskers here equate to about 90% of all the samples, so that's really the range. And then we have a few outliers that were quite different. And these are for the 5 compounds we measured that are known to be related to smoke exposure in the vineyard for grapes. Normally in grapes, these compounds are traditionally at 1 or lower. So you can see based on some of these whiskers, we certainly had grapes that were what would be considered for a normal year, a non-smoke event year. But you can also see there were quite a few above 1, with some extreme ones getting above 2.5. So these outliers in particular here and here that certainly had quite a lot of smoke exposure. If we look at the total smoke phenols in wine, so this is those free and bound within wine. Again, the biplot does the same. So here's sort of the average for the year and this range with these outliers outside of what's normal for it. What we've found I didn't put up what's normal because it depends on the grape variety, and I'm going to go into this future, but certainly above 20 would be higher than normal. And as you can see, particularly up here where we got close to 190 micrograms per liter of guaiacol, these are very high in those. So the grapes were high in compounds, and that was expressed in the wine as well. My thought was to look at things by varietal because we had a number of different compounds. And this, we're looking at the free smoke compounds in grapes for the white varietals that we had. So down here, it was the blue was Chardonnay, orange Pinot Gris, gray Riesling, and yellow Viognier. And I have the N down here because it is important to realize how many samples we were looking at for it. So this is a bar chart of the average with the standard deviation across. As we can see, for most of the compounds here, Chardonnay was the least. And then Pinot Gris, with Pinot Gris having quite a bit of guaiacol in it. If we look at the free smoke, that actually corresponded to the free smoke with Pinot Gris again having quite high levels of that in the finished wine there. And this bar in particular is quite high. I did find some baseline measurements from some white varieties. So this is grapes that were measured in years where there was no smoke. I do want to point out these numbers are from fruit that was not grown in the United States. So there can be some different terroir differences and potential clone differences, but at least provide some information. And I've chosen to provide baseline data on guaiacol and Au Cresol because these are the ones that are actually traditionally found at higher than 1 in grapes, whereas for methyl guaiacol, P. cresol, and M. cresol traditionally at 1 or below. So if we compare some of these, particularly for Chardonnay, so Chardonnay was definitely found above its baseline of 1 gram per liter. Pinot Gris was much higher, so the baseline was normally around 1.4. Riesling was higher than its 1.8, and unfortunately we don't have numbers for Viognier, but based on its variety, I'm sure you consider it fairly similar to Riesling. And for Au Cresol, again, you're, at least for Pinot Gris, and potentially a little bit of Chardonnay above the baseline there. So we're certainly seeing impacts. The one question we have now is at what concentration is it negative for that? If we look at the wine, so this is total smoke of wine. So the total potential risk you could have. And again, Pinot Gris having the greatest here. Up at about 100 micrograms per liter. If we look at the baseline for wine, so I just showed grapes, but this is the baseline found in wine. They are all above the baseline for guaiacol. And for Au Cresol, they also are above what we know for the baseline. But as I said before, not sure what the impact would be, particularly on these, or Chardonnay and Viognier. Pinot Gris and the Riesling are quite high from a sensory perception standpoint. So that would certainly be impacting the wine in some way. If we look at free smoke compounds of our red grapes, and we had more red varietals than white varietals, you see that variety certainly makes a difference. So this is, the first one is Cabernet Franc, then the orange is Cabernet Sauvignon, gray is Gamay Noir, yellow is Grenache, light blue is Merlot, our green is Pinot Noir, dark blue is Syrah, and then our brown is Tempranillo. And you can see we primarily had a lot of Pinot Noir samples, 35. The other ones are less, with our Cabernet Franc only having 1. But what you can see from a grape standpoint is the Cabernet Sauvignon, at least the samples submitted, had very little smoke exposure. It's below 1 here. And actually there are a number of varieties that are below 1. Tempranillo was below 1, the Gamay Noir was below 1. And we do know that sort of 1 and below for reds particularly is not affected by grape exposure. I will say that the Syrah here is not necessarily different. Syrah is known to have a lot of these compounds naturally, not because of smoke. So this potentially, of the little bit I've seen, is not necessarily problematic here. But we'll know when we go look at the wine, because the wine measurement was a sort of shows what happens after fermentation with that extraction. So if we can see here, just looking at free smoke, unfortunately for us in Oregon here, the Pinot Noir, despite the fact it didn't necessarily have the highest in the grapes, certainly showed the highest in the free smoke in the wine for this, followed then by Merlot, Grenache, and the Syrah for it. For the most part, the Cabernet Sauvignon, Tempranillo, and even potentially Cabernet Franc would be considered not impacted from a free smoke standpoint. And for the baseline data for Guaiacol and Haut Cresol, again, these were grapes were not grown in North America, but for Guaiacol, you're looking at a baseline of about 3.7. And this is sitting at around 4, so that would suggest this Cabernet Franc was not necessarily impacted. Grenache at 2.1. Our Grenache is the yellow, so it definitely did show some increase from smoke exposure. Merlot, which is our light blue at 5.2, that's pretty close. Though, of course, the range here shows that some were lower and some were higher, but the average at least was fairly close. Pinot Noir has a baseline of 3.4, and as you can see, our Pinot Noir was much greater than what is normally in the baseline. And Syrah baseline is actually around 12 micrograms per liter. And this was below that. So unfortunately for here, the Pinot Noir in particular is above at least the known baselines from wine from outside of the United States. If we look at the total now, which is really that complete risk over time, we see that the trend is a little different. So despite the fact that Pinot Noir had the greatest free smoke, it certainly didn't have the greatest total smoke. The greatest total smoke was really found in Grenache and Merlot. So even though the Grenache and Merlot looked like it might be fine from a free standpoint, as these wines age, they have the potential to develop more of those smoky aromas. And again, I found baseline for total numbers in wine, and almost all of them except for the Cabernet Sauvignon and the Tempranillo are above the baseline, or years that didn't express wildfire for it. So these grapes were impacted. They did absorb smoke. Clearly, each variety absorbed smoke a little differently. The question is, at what level is it really having a negative impact on wine? And from the one paper that was done on thresholds, particularly for Guaiacol, people start noticing a difference above 20 for it. They unfortunately only looked at that compound singularly, so we don't know what happens when it's put in a group with everything else. But if you're sort of above this 20 line, it is anticipated you are going to start noticing things in your wine. We thought it would be interesting to see how things compared within a region. So some of the samples, based on the information submitted, I was able to find ones from a similar area within a region. So you can see that they would have had more similar smoke exposure compared to if we look at everything across the state, how the varietals really change based on the smoke exposure. So this is region 1. And we had samples that were Syrah, Pinot Noir, Riesling, Cabernet Sauvignon, Chardonnay, and Grenache. And you can see the Pinot Noir definitely absorbed the most of the smoke compounds here. So again, total smoke compounds in wine. Then there was Syrah, and this is above the known baseline for it. And then Grenache, then Riesling. But our Cabernet Sauvignon and Chardonnay were certainly lower. So again, very similar smoke conditions, but the varieties are definitely absorbing things in a different manner. And there's other research that supports this as well. If we look at another region, it just shows some slightly different things as well. So this is a different region from that first one. And we're looking at Pinot Noir, Chardonnay, Riesling, Gamay Noir, and Pinot Gris. And you can see for what happened with the varieties that the Pinot Noir absorbed the most total smoke compounds, followed by the Riesling, and then the Pinot Gris. But actually, for some of these other smoke compounds, particularly Haut Cresol, Riesling absorbed the most of that. So as with our first one, the different varieties certainly absorbed different amounts of smoke compounds. But what can clearly be seen here is the different varieties also absorb different amounts of the different smoke compounds, if that's not a confusing statement right there. So it's as we've suspected, and some previous research has shown, one size does not fit all. You can have different varieties in similar locations that will absorb different compounds. And we found grapes that had what would be considered very similar to normal amounts of these smoke compounds, so similar to years that didn't have smoke, as well as clearly samples that had quite a lot of smoke exposure and absorbed quite a lot of those compounds. And I've just put our information up here if you have any questions. So myself and Michael did the chemical analysis, and James did the wine fermentations for us. Thank you for your time.
Hello, everyone. I'm Michael Chen from Oregon State University. We all know 2020 is a challenging year. On top of everything else, the industry suffered wildfire and smoke. Volatile phenol have been associated with smoke. The major volatile phenols, guaiacol, 4-methyl-guaiacol, O-cresol, M-cresol, and P-cresol. These volatile phenols can be in free form or bound form. The bound form can be converted to free form during fermentation, aging, or during drinking. When smoke comes, fast turnaround is everything. To respond with the industry's concern on smoke exposure, my lab quickly developed an analytical protocol to analyze volatile phenols based on SPME GC-MS technique. We can analyze the volatile phenols in about 30 minutes. We also developed a protocol for total phenol analysis in wine. To compensate with the difference of wine and their impact on analysis, we used the stable isotope labeled compounds as the internal standard for quantification. The isotope internal standard have the same structure as the corresponding volatile phenol, except that the hydrogen items are replaced with a heavy hydrogen, or we call the deuterated items. Using this technique, we achieved excellent linear calibration curves for all phenols and have a very low quantification limit. For free volatile phenol, we had the quantification limit down to 0.1 microgram per liter for free and 0.01 microgram per liter for some of the total phenols. Before we analyzed the samples, we collaborated with an Oregon winemaker and sent one set of micro-fermented wine samples to a certified commercial lab for testing. And we analyzed another set. As shown in the table, our data are exactly the same as those from the commercial certified lab. In our lab, we set up very strict analytical protocols to make sure all our analytical data are reliable and accurate. We run a check example for every 20 analysis to check the recovery. We also run duplicate analysis for every 10 samples to make sure the instruments are working and properly. To better understand the impact of smoke on grape and wine, OSU smoke team responded very quickly and worked very closely with the growers and winemakers last year. We collected a different variety of grapes across Oregon. Elizabeth did a grape analysis, and James did the fermentation, and my lab did the wine analysis. We did both the free and the total analysis. We analyzed about 80 samples. For the free phenols, the average guaiacol concentration was 12.8 microgram per liter, and the maximum reached 88 microgram per liter. For the total phenols, the average guaiacol was 43.6 microgram per liter, and the maximum was 197 microgram per liter. Elizabeth and James has already reported all the data in very detailed already, so I will not repeat the analysis. Separately, my lab analyzed 86 Pinot Noir wines from 2013 to 2016 to get baseline information. All the wines were made commercially in industry scale and no barrel aging. For these normal wines, guaiacol had an average concentration of 6.8 microgram per liter, with a range from 2 to 13 microgram per liter. We further investigated the concentration distribution. It demonstrated the number of samples in a concentration range. For example, 16 samples have a guaiacol concentration in the range 4 to 5. In this range, have 16 samples falling in this range. It is interesting to note that guaiacol and all cresol concentration distribution have a somewhat symmetric distribution for this control wine. For total phenol in normal wines, we found guaiacol had an average of 18.5 microgram per liter, which also matched with the median with a range 8.6 to 25 microgram per liter. So somewhat normal distribution observed for guaiacol, P cresol, as well as O cresol. When the wildfire happened last year, we analyzed 337 smoke-exposed red wine, 91 smoke-exposed white wine. These wines were compared with 86 control wine from different years. As you can see from here, smoke-exposed red wine represented the biggest dispersion of the data. Similarly, the total phenol, smoked exposed red wine represented the biggest dispersion of the data, and the P cresol exhibited the highest difference. And the P cresol, as you can see from here. Univariate data analysis was performed to establish a difference between control and smoke-exposed red wine. Total P cresol is the most discriminating compound for smoke exposure, followed by free OPM cresol. With the exception with free 4-methyl guaiacol and the total M cresol, all compounds were significantly higher in smoke-exposed wine. After hydrolysis, the total P cresol presented the most significant difference, as you can see from here. Heat map is used to identify the coordination of compounds. This value ranges from -1 to 1. As shown in the heat map, all the correlations are positive, ranging from 0.34, the blue one, to the deep red, 0.94 for guaiacol-free form versus bound guaiacol form. We further look at the ratio of free guaiacol to full methyl guaiacol. Both the control and smoke exposed wine are very similar, but the smoke exposed wine have some more centered distribution. The ratio of total guaiacol to total full methyl guaiacol in smoke exposed wine was lower than the control wine. Total guaiacol to free guaiacol ratio is slightly higher in smoke exposed wine. We are still searching for some type of parameters to differentiate smoke exposed wine from control wine, and this work is still underway. We are currently using high-resolution LC mass spectrometry to investigate smoke precursors in wine. We are using the latest metabolomics approach with data analysis. Using this technique, we have analyzed 14 commercial wines and 26 smoke-exposed wine by LC-MS. We have positively identified guaiacol and cresol glycoside in smoke-exposed wine by LC-MS. We also obtained more than 4,000 ions by MS-MS. PLC analysis here can clearly show that a controlled wine and a smoked wine are well clustered. Controlled wine is here with smoked controlled wine. We are continuing with data mining to figure out underlying relationship. I wanted to thank Oregon Wine Board, American Vineyard Foundation for funding. And Dr. Yan Ping did the smoke testing, performed all smoke analysis, total smoke analysis, and Ray Wen did a free smoke analysis, and Nin also helped with the project. Dr. Armando did a statistical analysis and LC-MS analysis. And thank you for your attention.